4, 3, 1. Good afternoon, and welcome to the Carnegie Observatories 2021 Astronomy Lecture Series. My name is John Mulcahy. I'm the director of the Carnegie Observatories and the Science Deputy for the Carnegie Institution for Science. We're streaming tonight's lecture live from the Huntington Library, unfortunately without an audience. We do hope we'll be able to have many of you back in the audience for next year's series. But we do thank you for joining us online this year. You may notice that I'm sitting down in a chair to do my introduction, and so I did have a little mishap a couple weeks ago and unfortunately broke my ankle. So I'm stuck with this boot on my foot for the moment, so apologies for that. Hopefully I'll be on my feet before the end of this year's series. We actually have a really great series for you this year. Tonight we're going to hear about dark matter. Next time we're going to hear about black holes. We're also going to hear about early galaxy formation and evolution and binary stars. So these are really some of the hottest topics in astronomy in this year's series. So we do hope you'll continue to join us for the next 3 after tonight. I want to acknowledge the Norris Foundation for their support of this series. They've supported us for many years on this, and it really makes this series possible. I also want to thank our friends here at the Huntington for hosting us, particularly in this COVID time, for allowing us to be here and do this for everybody. And they are providing the live stream. So thank you very much to them for their partnership through the years. Now on to today's speaker. Dr. Andrew Benson joined the Carnegie Observatories as a staff member in 2015. Prior to that, he was the George Ellery Hale Scholar in Theoretical Astrophysics at Carnegie. So he's been at Carnegie for a few years now. Andrew is a theoretical astrophysicist, best known for his work on really galaxy formation and evolution and work on dark matter. And he's created one of the most important, perhaps the most accurate models for galaxy formation known as Galacticus. Tonight he's going to be talking about his other real big interest, which is dark matter. And so with that, one more thing before I forget. You've seen on the screen behind me, you can see ways to ask questions. So I encourage you to ask for questions and vote for questions. And at the end, we'll try to have Andrew answer as many of those as possible. So with that, let me welcome to the stage Dr. Andrew Benson. Andrew.
Great. Thank you, John, for that introduction. And thank you to everybody out there watching online for joining us this evening. It's always a pleasure to be here. I really enjoy giving these lectures. And when I was asked to give this lecture this year, I went back and looked, when was the last time I gave one of these talks? And it turns out it was 7 years ago. So it's been quite a while. If any of you were with us then, you may remember I was talking and telling you about our planned searches to try to understand the nature of dark matter. And the great thing about it being 7 years since then is that we've actually made quite a lot of progress. So what I'm going to do tonight is kind of update you on where we are and show you some of the exciting new results that we've been able to obtain. So with that, I'm just going to dive right in. The first thing I want to do is just remind you what our universe is made of, because it's honestly a pretty weird place. So this is a pie chart that just shows us the 3 main components of our universe. And so this yellow sliver up at the top here that I've labeled baryons, that's everything you're familiar with, the normal matter, everything around you, your own body, things like carbon, hydrogen, nitrogen, oxygen, all of the normal stuff that we're used to thinking about. But you can see it's only like 4, maybe 5% of the total content of our universe. So it's a very small amount. The remainder of our universe is split between 2 unknowns. The first of those is called dark energy. That's that big red slice of the pie here. I'm not really going to talk about dark energy tonight, even though it's close to 70% of the universe. We don't really know what it is, but we know that it's causing the expansion of our universe to get faster and faster with time, to accelerate. We've known about this for about 20 years now. What I'm going to focus on, though, is this blue slice of the pie, the dark matter. So dark matter we've known about for much longer, for close to 50 years at this point. We still don't know what it is. We expect it's some kind of subatomic particle, not a particle that we know about, not one we've identified, but we think that's the most likely explanation for it. And dark matter seems to be everywhere. Some of the earliest evidence of this came from Vera Rubin, who was an astronomer at Carnegie, and who showed that dark matter is present in all galaxies, and we now know it's present throughout the universe. So even though we don't know what dark matter is, we do have some models for it. We have some ideas. And what I'm going to do is talk you through one of the, perhaps the main model for what dark matter is. And that's known as the cold dark matter model. And what I want to do is show you just how successful this model is to begin with. So what we're looking at here is a map of the light left over from the Big Bang, the explosion that started our universe almost 14 billion years ago. Now that explosion was incredibly hot, but since then the universe has expanded and cooled, and the light from that explosion is now actually very cold. But with satellites like the Planck satellite here, we can actually map that light, that radiation from the Big Bang, and make maps like this. What we're actually looking at here are just variations in the temperature of that light. And these variations are tiny. They're a fraction of a degree. So it's almost the same everywhere, but there are these very small variations. And so we have some spots that are a little warmer, some that are a little colder, and you get this kind of splotchy pattern across the sky. There's a couple of things you might notice about this. The first is that there are changes in temperature on a variety of different scales. Like here's a pretty big cold patch, but we also see just little cold blobs embedded inside hotter regions. And your eye might also pick out that there's kind of a characteristic size to these splotches. For example, if we pick one out up here, it has a particular size. And it turns out this is a map of the whole sky, and that size of that little splotch is about 1 degree of angle. So why am I showing you this, and what does it have to do with dark matter? Well, we can measure the size of these different variations in temperature, and then we can make a graph of them. Now, I feel bad because I'm a theorist, and I realized I didn't put any equations in this talk, which you're probably expecting equations from me, but I do have a lot of graphs at least. So, and when I show you these graphs, you don't need to worry too much about the details. I'll walk you through the key points and tell you what we're looking at. So what we're looking at here is just a measure of how big those variations in the temperature of the light from the Big Bang actually are. So on the vertical axis here, we have the size of the change in that temperature. So the further up you go, the bigger the change in the temperature. And then on the horizontal axis, we're looking at very large scales, so those biggest scale changes in temperature. And then over on the right, we're looking at small scales, changes that occur across very small angles. And you'll notice right away that there's a very clear peak here. And it turns out this corresponds to that angle of 1 degree that your eye was able to pick out from the previous image, and that's where the largest changes in temperature occur. So the red points are what are measured directly from the sky by the Planck satellite. So those are the actual measurements from the Big Bang. This blue line is a prediction from a model of dark matter, the so-called cold dark matter model. So this is really the simplest model of dark matter you can think of. The dark matter particle is very massive, which means it doesn't move around very quickly. That's why we call it cold. And it really doesn't do anything else very interesting. It doesn't interact with other particles. It doesn't interact with itself. It doesn't change with time. All it does is produce gravity. So it's the simplest possible model of dark matter. And you can see that the prediction from that, the blue curve, goes right through the measured points in almost every case. So this means this model is extremely successful at explaining these observations of the Big Bang. So that model works extremely well, at least on these very large scales. These are kind of cosmological scales, scales comparable to the size of our entire universe. So that's a big success for this model, but as scientists, we're never really happy with that. We always want to push a little further. So what if we can look down to somewhat smaller scales? Before I do that, let me show you a visualization of this dark matter. So dark matter doesn't emit light. That's why we call it dark matter, after all. But we can actually calculate how it would look if we're able to see it. And we do that by running computer simulations. So in this simulation, which was carried out by the Virgo Consortium, what they did was to take a really big supercomputer, and you feed it with information about how gravity works, so the laws of gravity, and then you feed it with a bunch of particles that represent dark matter in the universe, and you have that supercomputer go and calculate where all of the particles will be, how they move around with respect to each other, and where they would be at the present time. And then because this is a computer simulation, we can kind of break the laws of physics a little bit and say, well, what would happen if dark matter did emit light? So we could actually see it with our telescopes. So it doesn't in reality, but we can pretend that it does in our simulation. And it would look something like this. Now, this is a pretty big patch of our universe. It's about 2 billion years across, 2 billion light years across. And you can see we get this wonderful detail. So we get these little bright blobs here where there is a lot of dark matter collected into one place. That's because the dark matter's gravity, its own gravitational pull, has pulled a lot of dark matter together, made a dense little blob that we call a dark matter halo. And those would be the sites that galaxies eventually form in because the gas that galaxies are made from also gets pulled into these regions. And then connecting them, we have these kind of filamentary structures that we call the cosmic web. And then in between, there are these almost empty void regions where the dark matter has been essentially sucked out of to form these dense dark matter halos. So on large scales, this works very well, but let's come down to smaller scales. And I'm an astrophysicist and a cosmologist, so small scales to me are scales of the Milky Way galaxy. So actually still pretty big, but much smaller than the size of the whole universe. So on the left of the screen here, what you're looking at is another computer simulation, done in the same way, but now we just simulate a region around our own Milky Way galaxy. And once again, we light up the dark matter so you can see what it would look like if it were to emit light. So our Milky Way would actually form way down here in the center. It would be a pretty tiny little speck in this image. But you'll notice that all around, throughout this region, there are lots of other dense dark matter halos, regions where dark matter is collected together under its own gravitational pull. And remember, I told you that these halos are the sites where galaxies like to form. So you might guess by looking at this that there should be thousands or tens of thousands of galaxies close to our Milky Way, in fact, orbiting around it. And if you've ever been to the southern hemisphere, you might have actually seen a couple of such galaxies, the large and small Magellanic Clouds, which you can see in the night sky in the southern hemisphere. And it turns out that there are actually a whole bunch more. They're all too faint to see with the naked eye, but with telescopes we can find them. And we keep finding more. We know of something like 30 to 40 of these dwarf galaxies that orbit around our Milky Way. And in the right-hand panel, I'm showing you just a simple map of those. It's already a little out of date because, like I said, we keep finding more of these. But you just get some idea of how many we know about, 30 to 40. Our Milky Way's in the center here. Now, if you look at this, you might think there's a big problem, okay? On the left, we see thousands, maybe tens of thousands of dark matter halos, each of which could potentially form a galaxy. But we only see 30 or 40 galaxies around our Milky Way. So maybe the cold dark matter model, which was used to make this calculation, maybe it's wrong. And so this is actually something that I looked into almost 20 years ago now. And that explains why the graphics here are low quality. We didn't have fancy colors to put in our graphics back then. So it's kind of this grayscale. So it's a little retro looking, but still interesting. So what we're looking at here is just, I counted up the number of galaxies around the Milky Way. So on the vertical axis here, the higher up we go, the more galaxies we have. One galaxy, 10, 100. And then on the horizontal axis, I've just ordered the galaxies by how bright they are. So we have the brightest galaxies over on the right, and fainter galaxies over on the left. Now at the time, 20 years ago, the best collection of observed galaxies that we knew about had been made by Matteo a few years earlier. And so I took the measurements that he had made and the number of galaxies he'd found and just plotted them as these black circles. And then I ran a calculation based on cold dark matter, but also including all of the physics of how galaxies form, and calculated what we would expect based on that cold dark matter theory. And the answer was that we'd expect the results lie somewhere inside these kind of gray bands here. And so you can say it worked pretty well. So here were the known dwarf galaxies at that time. And yes, indeed, they do lie inside the gray region that our model predicted. So that was a success of the model. So the cold dark matter model still worked. And the reason it still worked is that even though there are thousands of these dark matter halos around our Milky Way, most of them are unable to form a galaxy. That gravitational pull is too weak to start pulling in the gas, the hydrogen and helium that is needed to form stars and to form a galaxy. So this model predicts those halos are there. We just can't actually see them because they don't contain a galaxy. So you may notice as well that while our model matched the data at the time, it also predicted that there should be a lot more as yet unfound galaxies. So it predicted there would be a whole bunch of fainter galaxies, in fact, a total of around 200 of them. So as a theorist, it's kind of my job to make predictions, but it's always a little nerve-wracking when you do, because as soon as you make a prediction, somebody else is going to go out and try to test it. And honestly, if you're wrong, well, that's okay. We still learn something from that. Even when the predictions are wrong, we then know that that model wasn't right, and we try to improve it and refine it. But I'd be lying if I didn't say that it's much more exciting when you get the prediction right, when you get the right answer. So let's fast forward to the present day. So this is the same kind of graph, just with nice modern colors and everything now. So again, number of galaxies, 1, 10, 100. And we're looking at faint galaxies over here, bright ones over on this side. The black line here, the solid black line, is now the number of these dwarf galaxies we know about from the Dark Energy Survey, which has made a much bigger and better survey of the sky now, and so has found more of these galaxies. And you can see that they've now found somewhere between 200 and 300 such galaxies. And then the colored regions here, the blue and the red, are predictions based on similar models that I did 20 years ago, but now updated, more modern. These are carried out by Oliver Newton and Ethan Nadler. Ethan will be joining us at Carnegie as a postdoctoral fellow later this year. And you can see they agree nicely with the data here. And in terms of my prediction, if I kind of overlay it and maybe flick back and forth between it, you can see that it was pretty much spot on. So we were able to predict successfully, using this cold dark matter model, the number of faint dwarf galaxies we expect to see around our Milky Way. So great, another confirmation for the cold dark matter model. But like I said, scientists were never really satisfied, so it works okay on very large cosmological scales. It works well on the scale of the Milky Way, but we still want to test it. So what about even smaller scales? And the reason we want to keep on going and keep testing is that we actually want to understand what the dark matter is made from. Like I said, we think it's some kind of subatomic particle, but what particle? What are its properties? How massive is it? Does it interact with other particles? We'd like to know exactly what this is, because if we did, we'd learn a lot, not just about astrophysics, but also about particle physics. And so fortunately, our particle physics colleagues are really good at coming up with a whole bunch of different ideas for what dark matter could be. So in this left-hand panel here, and this is from a nice review paper from a couple of years ago, what we're looking at is a collection of different proposals for what the dark matter particle could be. So each colored circle or ellipse here is a different hypothesis. And they've been ordered on the horizontal axis here in terms of their mass. So we have the most massive particles over here, the least massive on the left. And we're measuring them in funny units called giga-electron volts. So particle physicists like to measure masses as energies. And that may seem a little weird, but you've probably heard of E equals mc squared from Einstein. The E there is an energy, the m is a mass, so it tells us that mass and energy are related. And so we can choose to measure masses as energies if we want, and particle physicists do. And then on the vertical axis, what we have is a measure of how much these particles interact with themselves or with other particles. And so up at the top here, it would mean those particles interact with each other very strongly. Down at the bottom, it means they barely interact at all. They barely even notice each other. And so we've got a whole bunch of weird and wonderful ideas for what dark matter could be. So we have models where there are dark photons, sterile neutrinos, gravitinos, axions, fuzzy dark matter. This is even just a small sample. There's a huge number of possible theories for what the dark matter particle could be. And so we'd like to test these. We'd like to test whether these are viable models. And before we do that, since I'm an astrophysicist, we're going to try to do that using astronomical observations. We want to translate all of this over into a sort of a space where astronomy is the guiding principle. And so I've taken these same models here, and what we're looking at now is them organized in terms of their effect on things that we might be able to measure astronomically. So on the horizontal axis, what we're looking at is the mass of a dark matter halo where these different types of particle would begin to look different from CDM. So on very large scales, all of these particles produce results that look just like the cold dark matter model. They kind of have to because we know that on the largest scales in the universe, the cold dark matter model works well, so any viable model has to match it on those scales. But as we go down to small masses, low dark matter halos, things will begin to differ. Some of these different particle models will produce different results than cold dark matter. And so this is just a measure of what mass scale we would have to look at to start to see those differences. And then on the vertical axis, what we're just looking at is how frequently these particles interact with themselves or with other particles. So up here we have particles that interact very frequently, and in fact they interact so frequently that their behavior changes substantially over the age of the universe. And then down here at the bottom we have things which barely interact with each other or anything else at all. And in fact they interact so slowly that we can just ignore those interactions because they essentially just never interact in the entire age of the universe. And so what I'm going to do for the rest of this talk is just pick out one of these models to focus on so that we can test it and see what we can learn about it. And I'm going to choose this blue ellipse here, this thermal model. So I've been talking about the cold dark matter model, and I said it was cold because the particles are very massive and they don't move around very quickly. So the simplest possible change we could make to that is just to say, let's reduce the mass of the particles, and now they will begin to move around a little bit faster. And we call those models warm dark matter. And that's why this is labeled thermal. We had cold, warm, so it's all about the temperature of the dark matter here. So let's see what we can learn about these warm dark matter models. So here again is a simulation carried out by Sarnak-Bose a few years ago. And this is looking at a region around the Milky Way once again. And we're lighting up the dark matter. We're using a different color scale here, but it's the same idea. The Milky Way would be forming down here. And you see in the cold dark matter case, these hundreds and thousands of small dark matter halos all orbiting around the Milky Way. Now on the right is the same calculation, but done using warm dark matter. Now, if you kind of defocus your eyes a little bit, these look almost the same on large scales. You see the same overall structures. But if you focus in, you'll notice that the warm dark matter case is missing all of that fine, detailed structure that you see in CDM. And that's because the warm dark matter particles are moving around quite rapidly. Gravity tries to pull them together, but they just want to shoot away again, and so it's difficult to confine them in one space. So on large scales, gravity always wins. It's always strong enough, it pulls them together and forms this big overall halo, but the small ones are unable to form. So if we want to test the difference between cold dark matter and warm dark matter, what we need to do is look for the presence or absence of these little dark matter halos. And so that's where we come to the part of the story where we actually try to do this. And I think this is actually a really nice story because it's kind of the story of modern science, and that is that we have to involve large groups of people with varying expertise in order to make progress on these difficult and challenging questions. And so, in particular, for this work that I'm going to describe, we had to bring together expertise in astronomical observations, in dark matter theory, and also in data analysis. And so there's a whole group of people involved in this work. I've highlighted the ones who are either at Carnegie or will be coming to Carnegie soon, highlighted in red. And so let me walk you through each of those three areas of expertise and how they've contributed to this. So in the observations, the technique that we're using to try to understand the nature of dark matter is called gravitational lensing. So let me explain what gravitational lensing is. I'm sure you're all familiar with the concept of a lens. So here's a magnifying lens. If you have some small text you want to read, you hold this lens in front of it. The light passes from the page, passes through that lens. It becomes focused and magnified, makes it easier to read the text behind it. And so here is just the shape of this glass, which is creating a lens. But in principle, any piece of glass could be a lens. So here's another example. This is a wine glass, and we're looking along the stem of it. And if you happen to have a wine glass nearby, make sure it's empty, but then you can try this yourself, hold it up to a light, look along the stem, and here we're looking at a green LED behind this wine glass. And you can see, in this case, the lens that this wine glass creates has actually made multiple images of this background light. So it's made multiple images of a single object. Now, the reason I'm showing you this wine glass case is that it works actually kind of similarly to a gravitational lens. So in a gravitational lens, we have a situation something like this. So here's the Hubble Space Telescope, and it's trying to observe a very distant galaxy in which a supernova explosion just happened. But in this case, between the Hubble telescope and that supernova is a very massive, large galaxy. And the gravitational pull of this galaxy acts as a lens. Just like light passing through the glass of the magnifying lens, its path was curved and focused. The same thing happens with the light from the supernova. It can travel past the lens here, its path is curved, and it arrives at the HST. And it can do that and get to the same telescope in multiple different paths. And so what you actually see in this case is multiple images, in this case 4 images, of this distant supernova. So that's how a gravitational lens works. And what we're looking at here is kind of a perfect lens. But what if the lens was not perfect? To go back to our wine glass analogy, suppose now you have a wine glass which was not so high quality. Maybe you bought it in grad school when you were a poor student, and so it has some defects. Maybe it has some bubbles of air in there which were never gotten out of in the production of that glass. If you look along that, and if one of those bubbles of air, one of those defects, happens to lie close to one of the lensed images, it will distort that image, change its shape, maybe make it a little brighter or fainter. And we can have a similar effect happen in gravitational lensing. There can be defects, or dark matter halos in this case, which happen to lie along the path between the telescope and the thing we're looking at. And even though these are very low mass compared to our main lens galaxy, they still produce some gravitational pull, and so they will still distort the path of this light just a little bit. And that allows us to detect their presence. Even if this is a dark matter halo, which is invisible, we can't see it, we can tell it's there by looking at this, how it affects the light of this lensed image. So in this example, I used a supernova. In practice, in the work we've been doing, we actually look at distant galaxies that are being lensed. And so let me just show you, before I do, I wanted to point out, we have different types of dark matter halo here. We have what we call line of sight halos. These are ones which just happen to lie between us and the distant galaxy. But we can also have things called subhalos. So that's a halo which is orbiting around this bigger galaxy. And that will be important a little later. So let me now show you an actual image of one of the gravitational lenses that we've used for this work. So this is work led by Anna Nierenberg at UC Merced. And this is one of the lensed images of a distant galaxy. And you might not be too impressed by this. It looks very pixelated. But I can assure you this took a lot of Hubble Space Telescope time to get. These systems are very faint, very small. It's really difficult to collect this data. And you can see there are 4 images labeled A, B, C, and D of this distant galaxy. And there are a couple of things we can measure from this image. First of all, we can measure the positions of each of these images. And that will turn out to be very important. And we can also measure how bright each of them are. And maybe you can just see that image C, for example, is just a little bit fainter than the other ones. And we don't have just one of these. We actually have several. Here's 8 examples. We actually have a few more now as well. But in each of these, they look kind of more or less the same. You see 4 images in most of them. Their positions are a little different brightnesses. But we call these quad lenses, where there are 4 images of the background galaxy. Okay, so back to our first example image. I said we can measure the position of each of these 4 images. That's really useful because when we do, it actually allows us to learn a lot about the galaxy that is causing the lensing. And that's really crucial because we need to be able to model how that galaxy is causing lensing in very precise detail. And so by measuring the positions of these images, that allows us to do that. once we've then built a model of that lens galaxy, we can predict how bright each of these 4 images should be. And most of the time, that prediction works out almost perfectly. But occasionally, it turns out one of these images will be a little bit brighter or sometimes a little bit fainter than the others. So here's our prediction for how bright these 4 images should be, but occasionally, one of them will look a good deal brighter. And when that happens, we know that we have a defect in our lens. We have a small dark matter halo that happens to lie near one of our images that is causing it to look just a little bit brighter. And so if we can measure how bright these images are, we can then attempt to figure out where this dark matter halo is and how massive it is, and maybe then use that to tell the difference between cold and warm dark matter. But in order to make that connection, we need to do the astrophysical theory to understand how we connect what we observe with the Hubble Space Telescope to the particle physics properties, the mass of the dark matter particle. And the way we often do that is by running big computer simulations. I already showed you some of these, but here's one that's actually animated. So we're seeing the formation of a dark matter halo starting from close to the Big Bang and progressing toward the current day. So there's a couple of things you'll notice about this. So first of all, it's really beautiful. Again, you see this cosmic web of structure that's interlinking. You'll see dark matter halos forming. In a minute here, you'll see down in the center a really big halo begin to form, and you'll see halos merging together and orbiting around each other. So it's really beautiful to look at, but you can also tell that it's extremely complicated. There's a lot going on here. Interactions, things moving around, complicated shapes. That's why we use a supercomputer to solve the physics of what's going on. So that works really well, but there's one problem. It's very slow. So this took a very large supercomputer several months to calculate. Now, as you'll see in a few minutes, we need to do this kind of calculation not just once, but millions or tens of millions of times. And we need to do that for every type of dark matter we want to consider. And so it's just not practical. There's just not enough supercomputers in the world to allow us to do that. So what we have to do is really what the whole job of a theoretical physicist is, and that's take a complicated natural phenomenon like this and simplify it down into its simplest pieces so that we can understand it and perform the calculations quickly. So this is something that I've been working on for the past few years, and what I'm going to do is step you through some of the physics that's involved. Now, if you're paying close attention, you might realize that these are not dark matter halos. This is the Earth and the Moon. Why am I showing you the Earth and the Moon? Well, one of the other really cool things about physics is that the same physics applies on all different scales in our universe. So the physics of gravity, which is crucial for determining how dark matter behaves, is just the same physics of gravity that acts in our solar system on things like the Earth and the Moon and the other planets. So I'm going to talk you through some of the physics that we put into our models for the life of a dark matter subhalo, one of these halos that is orbiting around a larger halo. And I'm going to use analogies from the solar system that you'll probably be much more familiar with, just to show you that it's the same physics, just working on a larger scale. Okay, so we're starting out with the Earth and the Moon, and probably the main thing we know about the Earth and the Moon is that the Moon goes around the Earth. So once a month, it orbits around on approximately a circle and comes back to where it started from. And the reason it does that is because of the gravitational pull of the Earth. So the Moon's trying to move off in this direction. The Earth wants to pull it back, and so it eventually starts moving around on this circular path. It orbits around the Earth. Now we can replace this with a dark matter halo and its subhalo. And so here's a really simple diagram of what that might look like. This green circle is our large dark matter halo, and the red circle is a little subhalo that's orbiting inside it. And for exactly the same reason as in the Earth-Moon system, the subhalo is going to move around inside its host on a circle like this because it's being pulled toward the center by the gravity of this dark matter halo. There's one big difference, of course, and that is that this subhalo is orbiting inside its host. If the Moon tried to orbit inside the Earth, we'd all have a very, very bad day. They would collide. For dark matter, it doesn't matter. The particles don't really interact with each other in any way, so they can just pass right through each other. So the subhalo orbits around inside its halo. There are a couple of other things we have to include. So another effect is called dynamical friction. What does that mean? Well, as this subhalo moves around, its gravity is also pulling on the particles of dark matter in its host halo. And it kind of causes them to form into a wake behind it. So if you've ever seen a ship sailing on the ocean, it forms a wake of kind of white water behind it. Same kind of thing here. And then that wake of dark matter that is produced behind the subhalo has its own gravitational pull, and it wants to pull back on this subhalo. And if you've ever seen an athlete training, and sometimes they attach like a little parachute behind them so that when they run along, they get some drag from that parachute. It makes it more difficult to run. They become a better athlete. Same kind of thing here. We get a drag force on the subhalo that steals energy from its orbit. And as a result, it begins to sink in and spiral in toward the center of its host halo. Okay, two more effects that we include. The next one is tidal forces. So let's look at a solar system analogy again. So here's the Earth and the Moon. We've already said the Moon goes around the Earth because of the gravitational pull of the Earth, but the Moon also pulls gravitationally on the Earth as well. And in particular, because our oceans are made of water, which are easy to move around, we find that on the side of the Earth closest to the Moon, the ocean water is pulled up a little bit toward the Moon. On the opposite side of the Earth, where the Moon's gravitational pull is a little bit weaker, the water kind of falls away a little bit from the Moon. And so what you end up is with, on opposite side of the Earth, you get these tidal bulges in the ocean, which is why we get two high tides per day. Now, imagine if the Moon was more massive. If it was more massive, it would have a stronger gravitational pull, so the oceans would get pulled a little bit further toward it. If we kept making the Moon more and more massive, eventually the ocean water would just get pulled right off of the Earth, and it would stream away in both sides. Again, it would be a pretty bad day, especially if you were a fish, but a pretty bad day for all of us, I think. Same thing happens, same physics happens in our dark matter case. The tidal forces from our host halo pull on the dark matter in our subhalo and cause it to stream out from either side. That takes mass away from our subhalo. It loses mass over time and can eventually be destroyed. So one final effect that we include, and related to that, is what we call tidal shocks or tidal heating. So as the subhalo orbits around, the tidal forces it's seeing don't stay the same. They change over time. And that kind of stretches and squashes our subhalo and basically heats it up and causes it to expand. And again, we have an analogy to that in the solar system. So here's Jupiter's moon Io. Here's Jupiter. This is not the scale. But Io orbits very close to Jupiter, and it experiences strong tidal forces from Jupiter, and it experiences this tidal heating. And that actually heats up the inside of Io, and somehow that energy has to come out. And the way it comes out is through volcanism, through volcanoes. So Io is actually the most volcanically active object in our solar system, and it's because it's being tidally heated by Jupiter. So the same thing happens here. The subhalo is heated and expands. So those are four simple ingredients that we're going to try to use to explain all of that complicated behavior you saw in the video a few slides ago. So before we do that, we're going to run a much simpler simulation so that we can check whether this model actually gets things right. So we're just going to look at a single subhalo orbiting around in its host and see what happens to it. So this is work carried out by my postdoc, Xiaolong Du. And what he's doing here is simulating this dark matter subhalo as it evolves around inside its host. We're not showing you the host here just to keep things simple. But you can see every time it gets close to the center, we have tidal forces which pull off streams of matter from this orbiting subhalo. And here we're just focusing in on it. And you can see it's gradually shrinking over time. And we actually run this calculation for 37 billion years, so like 3 times the age of the universe, just to see what happens. And at the end, the subhalo is still there. It's lost most of its mass, but there's a little bit left. Most of its mass is now spread out throughout its host in these kind of beautiful shells and swirls. So then we can ask, how well does our model do at matching that calculation? So let's just look at how much of the subhalo's mass remains. So starting out at all of its mass, 100%, down here will be 0. And this is just the time that we've been running that calculation for, starting out at 0 and ending at 37 billion years. So the blue points here are measured directly from that calculation. The orange line is what we get from our simple model, including all of that physics that I just described. And you can see it's not perfect. It doesn't quite get the sharpness of these corners correct. But overall, over 37 billion years of time, it gets pretty much the right reduction in the mass of the subhalo. And importantly, it took us like a fraction of a second to run this orange line, this simple model, compared to a few days to run this full calculation shown by the blue circles. So it's much, much faster and almost as accurate. We can also start to do interesting things with these models, like ask what would happen if we ignored the tidal heating, if we just switched that off. And in that case, it would actually mean that the subhalo was able to hold on to its mass for much longer. So it's also interesting that we get to play with the physics and learn what happens. So it works very well in this simple case where we have just one subhalo, but we also want to ask how well it works when we have a whole system of subhalos like we'd have around the Milky Way or around a lens galaxy. So here's an example of that from the Caterpillar project, partly run by Carnegie postdoctoral fellow Alex G. And in work led by Shangqi Yang, who will also be joining us at Carnegie later this year, she was able to compare the predictions from that simple model. I won't go through the details here, but compare them with the results from this simulation, and in every case, they match extremely well. So we have a simple model that is fast and can give us predictions for where the dark matter subhalos should be, how massive they are, and how long they survive. Okay, final step, the data analysis. What we want to know is where are the subhalos and how massive are they? So here's our gravitational lens again. This image looks a little brighter. So we think there might be a dark matter subhalo here, but maybe it's over here, or maybe it's a little more massive and a little bit further away. We don't know exactly where it is because all we can do is see its effects on this lensed image. We don't see the subhalo itself. So how do we figure out where the subhalo is? Well, the answer is we guess. Now, we don't just make a completely random guess. We make a guess that's based on those theoretical calculations that I just described that tell us on average where we'd expect to find these dark matter halos. So it's an educated, very well-informed guess, but that's what we do. We guess where these halos should be. But we don't do it just once. We do it tens of millions of times. I'm not going to show you all 10 million examples, but here's 3 of them. So this is work led by Daniel Gilman. And what we're looking at here is one of these gravitational lenses. These green circles are the 4 images. The colors now show us how much magnification is being created by the gravitational lens. So in red, you'd have a high magnification. In the blue regions, we actually have demagnification. The image would be a little bit fainter if it was in one of these blue regions. And you can see, for example, here, next to this, one of the 4 images, we have this little red splotch of magnification because there happens to be a dark matter subhalo that we've placed right at this point. So I said we do this many times. We pick one set of randomly chosen subhalos here. We pick a completely different random set here and another set here. Do that millions of times, guided by the physics. So do this as many times as we can. And then we ask, how often does this get us the right answer? How often does this predict the correct magnification? And if our model predicts the correct magnification, we keep that realization. So this one is good, so we keep it. If it predicts an incorrect magnification, we just throw that case away. And then we repeat this for many different types of dark matter, cold dark matter, warm dark matter of different temperatures. And then we ask which type of dark matter gets the correct magnification most often. And so if a cold dark matter calculation gets the right magnification, say, 100 times out of this 10 million, but a warm dark matter case gets the right magnification only 10 times out of that 10 million, then we can say that the cold dark matter model is 10 times better, 10 times more likely at explaining these data. Now, of course, there's a whole bunch of math behind this which makes it very quantitative and precise, but that's the basic idea of what we do. So let me show you the results. So this is a new result. It came out just last year and tells us what we've learned about the nature of dark matter from this study. So let me explain what you're looking at here. So on the horizontal axis, what we have is the mass of the dark matter halo where the effects of warm dark matter start to show up, where things start to look different from the cold dark matter prediction. So far on the left here, this is where we would be if dark matter actually was cold. And way on the right is where we would be if dark matter was very, very warm. And then as we look up and down on this vertical axis, the higher up these gray bars go, the more likely that particular model of dark matter is. And conversely, the lower they are, the less likely it is. So you can already tell just by looking at this, that this whole region over here, where the bars are all very low, these are very unlikely. These models of dark matter cannot explain the magnifications we see in those gravitational lenses. Over on this side, the bars are all much higher. So these models, these types of warm dark matter are all consistent. They all predict the correct magnifications for our gravitational lens systems. And so we can basically rule out that dark matter could be as warm as this red region. And so if we translate that through all of that theoretical modeling that we did into a mass of the dark matter particle, what we find is that the dark matter particle must be at least 5.2 kiloelectron volts. So what does that mean? Because it's not very intuitive. It's a little difficult to describe because particles are so low mass. But to give you an idea, another subatomic particle that's much more familiar is the electron that's in all of the atoms around us. So the dark matter particle has to have a mass of at least 1% the mass of that electron. Could be much larger. We can't rule that out right now, but we know it can't be any less than that. And this is one of the strongest constraints we currently have on the mass of the dark matter particle. It's not a detection yet, it's not an actual measurement, but we're really starting to rule out a large part of the possible range of dark matter particle masses. So where do we go next? Like I said, scientists never want to give up. We want to keep going. Unfortunately, that's going to be something that we can do in the next 10 years. So first of all, as any astronomer will tell you, we always want more observations, and we're going to get those. So the Rubin Observatory, which is very aptly named after Vera Rubin, is going to be great at finding new lenses. The more of these lens systems we can find, the more measurements we can make, the more accurate our results will be. So this telescope will survey the sky down in Chile and find a lot of these lenses. And then on the right, we have the James Webb Space Telescope, which is hopefully going to be launched later this year. And it will be really good at measuring those positions and magnifications of the images that we need to test our models. And we were very excited just a couple of weeks ago to learn that we were awarded time in the first cycle of observations with JWST to make these kind of measurements. So that's the observations. There's work to be done on the theory side as well. I'm not going to go into too many details here, but if you remember way back at the beginning, I showed you that pie chart with the constituents of our universe and said that there was mostly dark matter, but there was also some of this baryonic material, the normal material. We've kind of ignored that so far. And the reason is that it's only 4% of the universe, so it's not a big factor. But if we want to get things right, we should really take it into account, because we do get things like tidal forces from galaxies as well as dark matter halos. So for example, tidal forces from the Milky Way or from a lens galaxy, and those can change the predictions we make for the number of subhalos that survive. So it's important to improve those models. And then also we can improve the data analysis. So in work led by Ethan Nadler, what we're starting to do is to combine results from different experiments. So what Ethan did here was to take the results we had from this lensing work that I just described to you, and then combine it with measurements of the Milky Way satellite galaxies. If you remember way back at the start of this talk, I was telling you we can use the satellite galaxies of the Milky Way to learn about the nature of dark matter. So Ethan took both of these measurements and combined them, and by doing so was able to find an even stronger constraint on the mass of the dark matter particle. We now know it has to be a little over at least 9 kiloelectron volts, so a much stronger constraint. And we plan to continue doing this, bringing in other data sets, other types of experiment and observation to find the best constraints that we can. So, to summarize, what we're trying to do here is to answer the question, what is dark matter? And I think this is clearly one of the biggest questions in all of astrophysics. And I'm probably a little biased, but I think it's really one of the biggest questions in all of science because it's such a large part of our universe. And learning about it will probably tell us not only about astrophysics, but also about particle physics as well. It will give new insights into both. So answering this question really requires a combination of different expertise. We have to have expertise in observations, in astrophysics theory, and also data analysis. Bring all of these things together, work together to reach that final answer. So like I said, there's been lots of progress. We're beginning to test some of the possible answers to this question. And that's really exciting. There's no final answer yet, but we're making real progress. And there is the real probability of getting a measurement, an actual detection, an answer in the not too distant future. And the reason for that is because we have new telescopes, new models, and new data analyses that will all be here soon. And so who knows, if I come back and give another Huntington lecture in another 7 years' time, hopefully we'll have some updates. Maybe we'll actually have a real detection and an answer for you. That would be super exciting. So I'm going to finish there, and I think we can take any questions.
Excellent. Thank you, Andrew. Thank you, Andrew, for that really interesting talk. It's good to see the progress on dark matter. And we have a bunch of questions, so I'm just going to jump right in, and we'll see how many of these we can get through. I'll remind you, you can vote on the questions online if you haven't. So the first question is dark matter everywhere? Do I have dark matter in me?
Oh, great question. Yes, as far as we know, dark matter is everywhere. All of the observations seem to confirm that it's everywhere in every galaxy we look at. It's everywhere throughout our Milky Way. And so we expect that it's also everywhere around us. So, and remember, dark matter doesn't really interact with normal matter. So a dark matter particle flying through this room, this auditorium, would just fly right through, pass through me, be passing through you. You wouldn't notice anything. But yes, so the answer is yes, dark matter is everywhere, and it will be inside you all the time.
Excellent, yes. This is an interesting question. Does dark matter have the same gravitational constant? In other words, the same strength per unit mass as normal matter?
Yeah, that's a really interesting question. So in Einstein's theory of gravity, that's kind of an assumption of Einstein's theory is that all matter, whether it's dark matter, normal matter, or anything else, has the same gravitational constant, the same strength of gravity for a given mass. So it's a little difficult to test that for dark matter. We work under that assumption. There have been some tests made, actually using, in many cases, those tidal streams of stars that we see from some galaxies. And to the best degree that we can currently measure it, the gravitational constants are the same. But those measurements are somewhat approximate, I would say, at this point. So it's not confirmed, but there's no evidence to the contrary.
Great, thank you. There's a question, has dark matter always been around, or was it created after the Big Bang, or has it been there since the start?
That's also a really good question. So we know it has to have been there from almost the start. So in the tiny fractions of a second after the Big Bang, a lot of things happened. We had a period of what's called inflation. Particles were created and destroyed. At some point, again, in a tiny fraction of a second, we assume that the dark matter was created at that point. We know that it has to have been there very early because we see its effect in the cosmic microwave background, as I showed right at the start of the talk here. If it hadn't been around at that point in the universe, which is a few 100,000 years after the Big Bang, then the model wouldn't get the right answer for what the cosmic microwave background looked like. So we don't know precisely when dark matter was created, but most likely in the very, very earliest fractions of a second in the universe.
So you made a really good case in your talk for the simple model, for doing a simpler model so you can run it many, many, many times. So there's a question which is kind of related to that, which is how increases in computing power will help with the search here. I mean, will the computing power reach up to a point where you could just do the sophisticated simulations millions of times over a day or something?
Yes, that's a great question. So more computing power always helps. We always want to run bigger and better calculations. And there's a very simple way we can do that, which is just by running more calculations. So instead of running 10 million of our realizations, we could run 100 million, and our answers would get a little more accurate. But perhaps more interestingly is with more computation, we can make the physics more realistic. We always have to make approximations, and we try to do that in a way which we approximate out the things that are not going to have a big effect on the answers. But with more computing power, we can actually put that physics back in, and our answers should then be more accurate. So I think we're a very long way from being able to do sort of a full first principles pure calculation just using a supercomputer without having to put in any real brain power and thinking. We're still a very, very long way from that. So unfortunately, we still have to keep working hard and thinking for the foreseeable future.
A couple people have been interested in understanding kind of what experiments are going on to look for dark matter. So these are, I think, things outside of astronomy. I don't know if you have any comments on those and how successful they've been so far.
Yeah, so there are a lot of experiments, what we call ground-based experiments, and they're typically actually far underground, often in old unused mines, because in order to detect dark matter, we need to actually shield it from all of the other cosmic radiation and noise that's just around on the surface of the Earth. And so those experiments are actually looking for the very occasional times when a dark matter particle will interact with a particle of normal matter and produce some measurable signal. So that's trying to actually detect the dark matter particles individually in a lab on Earth. Those experiments have been running for quite a long time, and there are many of them. So far, none of them have made a convincing detection of a dark matter particle. So that's still interesting and useful because it starts to rule out, just as we've done here, it starts to rule out some possible types of dark matter. But there's still a wide range of other possible types that, if dark matter is made of that type of particle, we just wouldn't have expected to find it yet. So those experiments are very important, and they're very complementary to what we do in astrophysics. As yet, no detections. The people running those experiments are also trying to make them bigger and better and more sensitive. So who knows? It's kind of a guessing game what dark matter is, and so you look where you can, and we'll see who finds it.
There's a question which is somewhat similar to the earlier question, but which is, why don't we see the effects, or aren't we able to detect dark matter within the solar system? So everything you're talking about here is on much bigger scales, right? So the question is kind of locally, do we see any impact from the dark matter?
Yeah, so that's a really interesting question. So our solar system, even though it seems like very empty, there's huge amounts of space between us and the moon and us and the sun and all of the other planets. But our solar system is actually a very dense place compared to most of the universe. And what that means is that within our solar system, the amount of dark matter is actually tiny compared to the mass of the sun and even the planets. And so any effect from it is going to be extremely small, extremely tiny, and pretty much just unmeasurable. There have been some attempts to try to detect whether dark matter would kind of pool in the center of the sun, and that could have some effects on the structure of the sun and its brightness. But there have been no successful detections of it that way either. So solar system measurements, just very difficult because there's so little dark matter around us.
Okay, and so I have just one fun question at the end, which is more of a personal question. Dr. Benson has an interesting accent. Tennessee? It's not from Tennessee.
That's an interesting guess, but no. I'm originally from England. My accent is some weird hybrid, and when I give a talk and I'm not hearing anybody else speak back to me, my accent tends to drift a little bit more back to my English accent, which I know my mom is watching me, so she'll be pretty happy to hear that, I'm sure.
Yeah, so not Tennessee, anyhow. Well, Andrew, thank you for that. There were many more questions, but we want to wrap up here. And just thank you for that update on dark matter. We will, of course, have Andrew back, hopefully maybe not 7 years, with some more exciting results. So with that, I just want to thank everybody for joining us today. Reminder, our next lecture is 2 weeks from tonight, and that will be Tom Holoing, who's a Hubble Fellow at Carnegie, and he'll be talking about black holes, another extremely interesting topic. So thank you for joining us, everybody, and we look forward to seeing you in a couple weeks. Thank you.